Okay, so last time we talked about some of the passive tectonic settings like cratons and passive margins like the east coast of the United States. There can be earthquakes along those, but they're rare. The most significant ones was maybe the one that was in Charleston back in the 1800s. It wasn't that passive margin, but we still have them on occasion here. So this section here, we're going to talk about the active tectonic settings. So these are really the ones that we need to focus on here in the class anyways. So there's really three types of settings, and they go based off of the types of stress or that we have, right? So there's basically three types of stress, and we have compression, we have tension, tensional stress, and then we have shear stress. So compression is when they're coming together, right? Two materials coming together. Tensional means they're going apart, and then shear means they're sliding past each other in a sense. And so the three types that you have, or the active stress that you usually have related to the plate boundaries here, is we have convergent boundaries for the compression, and then we have divergent boundaries for tensional stress, and then we have transform boundaries for shear stress, right? So those are basically three types of stress we have, and the boundaries in which they're related to from there. So what we're going to do now is I'm going to actually go through here and talk about each one of these and the types of plate boundaries that they have. And so we're going to start off with convergent first and discuss the different types of convergence that we have. So we have convergent boundaries here, and those convergent boundaries, there's basically three types of convergent boundaries, right? We have the two different types of plates. We have oceanic or continental. And so we have basically three different types of plate boundaries that you can have. Because if you have an oceanic crust, okay, and a continental crust coming together, you're going to have them interact differently. So let's have this thin oceanic crust here and a thicker continental crust. That's how it usually is. The oceanic crust is going to be have a lower density to it. I'm just going to do D for density. And the continental crust here is going to have a higher density. And because of that, you're going to have your oceanic crust is going to subduct down. It's probably not the best drawing there. Subduct down below our continental crust right here. Okay? And when that happens, right, oops. When that happens, oh, I messed up again. That continental crust is going to go down, the oceanic crust is going to, the oceanic crust is going to go down, the continental crust is going to stay up on top because of the different densities. And as it goes down, the crust goes down, you're going to have some things happen. First of all, you have, that's the water here, so you have the ocean there, continents there, and this material is going to, as it goes down, it brings water with it, right? So now you have an increase in water or volatiles in the material. But you also have an increase in temperature as it goes down. And so as you have that increase in temperature, that increase in volatiles, you start having a melt form. You're lowering the melting point, and so now that magma in the mafic mantle, you have a mafic crust here, so this is mafic. You have a felsic continental crust, and this material that comes up, because it's as it cools off, as it goes up, it's going to differentiate out the mafic material. So it becomes more intermediate over time, right? So going back to the different types of magmas, you start off with this mafic material, and then it goes to this, it's going to become more and more intermediate or more felsic over time. And so, as it rises through the crust, it will form a volcano, right? And that volcano, if you remember, if it's going to be mostly intermediate, okay, is going to be that stratovolcano, okay? So it would be good examples of some stratovolcanoes. So you can have a good example of this kind of setting might be the Cascades, okay, in northwestern United States. Maybe the Andes would be a good example of this. Both settings have these stratovolcanoes where you have the oceanic crust go down and then coming back up to form these stratovolcanoes. Okay, and so the magma is being formed or being melted because of the added water and the added temperature of the materials as it goes. Now in these settings you're going to have very large earthquakes. There's a lot of friction here, and so the earthquakes are going to be large. There are going to be lots of earthquakes, and they're going to be big. So they're going to be anywhere from, they can go all the way from up to a 9, some of the largest earthquakes, down to 2s or 3s or something like that. But the largest ones are going to be like between a 7 and a 9. So these large earthquakes, magnitude earthquakes that you're going to have in these areas. Okay, because there's lots of friction when you have convergence through here. Now, as in any convergent boundary, I'm going to just do some basics for any convergent boundary here. You're going to have both brittle deformation at the surface, so that's going to be shallow material. Okay, so that's going to be up in this region up here, right? Okay, but you're also going to have ductile deformation. Okay, which would be at depth. So that's going to be down in this area, down in here or something like that, or down in here even. Okay, so that's going to have ductile deformation. Now remember, ductile deformation, you're going to get folds. Okay, so you're going to get a lot, maybe a crust going this way, going to be converging together, and that's going to start to form into these folds, right? Okay, so now you have an anticline here, and a syncline here, and maybe another anticline here. I'm not going to do the whole thing, but there you go. Okay, so you have these folds being formed. You can also have structural domes and structural basins, but this is all ductile deformation, right? Because the reason you're getting ductile deformation is you have your higher temperatures in the subsurface and higher pressures as well, and therefore you get this ductile deformation. But if you have high temperatures and high pressures, that also means you're going to have metamorphism. Okay, and you're going to have anywhere from what we call low-grade metamorphism to high-grade metamorphism. Low-grade is going to be the lower temperatures and lower pressures, whereas the high-grade is going to be the higher ones. So you can get things like schists and a gneiss, whereas here in the low-grade you're going to get more slates and things like that. Okay, so all convergent boundaries get this ductile deformation and brittle deformation. We haven't talked about the brittle yet. Oops, do that over again. Brittle deformation. I messed up again. Oh, we got it. Okay, move it over. Oops, I messed up. Oh, wait, messed up. I wonder if I can do it back. We're still learning this here. Anyways, I messed that up bad, royally. Okay. Get out of the way. Okay, so anyways, you guys get the point here, I think. Let's see here if I can fix this here. I'm going to pause that. Okay, so I fixed that now, so hopefully that's a little bit better. So here's the convergence here, and you're going to get your ductile deformation. We talked about that already, where you get your folds. Okay, you get your folds here, and you get anticlines, synclines, domes, and bases, but you also get metamorphism. Okay, now when you have brittle deformation, which is going to be the shallower sections here, you're going to have faults forming, right? And because your convergence, you have the two materials coming together, you're going to get what we call reverse faults. Reverse, let me zoom this in a little bit. Reverse and thrust faults. Okay? And so, if you remember right, that means basically one block, I'm going to kind of draw this a little bit, is going up over the other block here, because you have this pushing in, okay? And so this is the hanging wall, if you remember right, and this is the foot wall, okay? And this block is going up above the other block. And so if this was in, I'm not very good at doing these in 3D, okay, but it'd be looking something like that. And there we go. So this block goes up, and this block goes down. So this is a dip slit fault, which means it's going vertical and going upwards and downwards as they're being pushed together. Okay, so those are examples of reversing thrust. And remember, the only difference between reversing thrust is the angle of the actual fault. Where thrust is low angle and reverse is high angle. But this always happens at convergent boundaries. So any convergent boundary is going to have this brittle faults of reverse and thrust, but they're also going to have ductile folds, and they're going to have metamorphism. So all of that's going to happen in a convergent boundary there. Okay, sorry about that. So also, when we have a lot of metamorphism and also igneous activity at convergent boundaries, we tend to then have a lot of geological resources. Okay, and the resources that are common because of the volcanics here are things like gold, silver, copper, nickel, stuff like that. Okay, so a lot of some of our precious metals come from areas like these, like these convergent plate boundaries, where we have lots of metamorphic and igneous activity. And so, so realize that these resources are at these localities. So let's finish off the different other types of convergent boundaries. We did the oceanic continental here, but we also have ocean, and that's when you have your ocean plate boundary, right, going underneath another ocean plate boundary. So this is ocean and ocean. They're both mafic. They both start off as mafic, right? But one of them tends to be older or denser than the other one, partially because they're from a source further away. Because you have to remember, divergent plate boundaries is where the material is formed, and then the the convergent boundaries is where the material is destroyed. So this is destroyed material, and same with here. This one's also destroyed material. Okay, material over time. So as this goes down, once again, you have a high increase in water, and then and temperature. And so because of that, you have the material rise up and form volcanoes again. But once again, you can find mostly going to be these stratovolcanoes. So places like the Aleutian Islands in Alaska, Japan is an example of this. When you have two ocean crests coming together to form these what we call island arcs. Okay, so we form what we call island arcs at these locations. Whereas in oceanic convergence, we call them volcanic arcs. Okay, and so that are forming these ones. And so here you tend to have this material tend to get stratovolcanoes, but you can also get cinder cones at either one of these, really, because if you remember right, looking at these, you're going to get these lower and intermediate materials at the ocean, because you're getting two mafic materials, and as they rise up, it's going to become more intermediate. But I purposely made a smaller volcano here, whereas these ones are bigger ones, because these ones are going to be more felsic, and these ones are going to be more intermediate. Okay, because they're going through mafic material, this one's going through felsic material, so as it goes up and changes, it's going to be a little bit thicker material and more stratovolcanoes, okay, or at the convergence. Okay, so good examples of these, like I said, Aleutian, Japan. You're also going to still have large earthquakes at these localities, but still going to be around a 7, maybe up to an 8 or even a 9, but still large ones. You have tsunamis associated with both of these, so you can have tsunamis here, also here. Anytime you have an earthquake of a plate going down, you're going to have potential tsunamis at these localities. Okay, now we're going to finish up the last one just because of time-wise on our next group, which would be our continent interaction. But these are the active